Hello everyone, and thank you for the opportunity that is being given to me today. So my name is Yesi Christie, and today I'm going to present some of the results of the study that we conducted about the evaluation of ECMWF forecast to predict daily and monthly solar radiation over Indonesia region. So the outline of this presentation is some background, data and method, results and discussion, and the last one would be conclusion. So one of the main motivation in doing this study is to create a solar radiation forecast product in order to support the application in solar energy sector. So previously, this kind of product, solar radiation forecast, uh, was not exist yet for Indonesia region. So this is actually one of the first few studies that assess the output, the performance of numerical model output to predict solar radiation in Indonesia. So today we're going to use one of the ECMWF products that is called the surface solar radiation downward. So to evaluate the output of the numerical model, here we use the ground observed radiation. So it is a parameter called global horizontal irradiance. So it's actually an instantaneous value in watt per meter square. So in order to make it more suitable to the application in solar energy sector, we have to convert it first into daily and monthly solar radiation. So the unit would be watt hour per meter square. And for now, we use the data from 5 stations only. And before using the data in the analysis, we applied a few quality control procedures to make sure the quality of the data. And here we use the data from January 2018 to December 2019. So for the ECMWF solar radiation forecast, as I mentioned earlier, the product that we use is the surface solar radiation downward, and it is in joule per meter square. So first we have to convert this value first into watt hour per meter square. And then this forecast is generated on the first day of every month for the next 7 months with a time step of 6 hours. And the spatial resolution of the data is zero point 0.4 degree. So to quantify the evaluation result, here we use several error metrics such as mean bias error, mean absolute error, root mean square error, and we also calculate the correlation coefficient between the model and the observed radiation. Here we also try to evaluate the forecast error based on cloud cover because solar radiation highly depends on cloud condition. So here to define the sky condition or the cloud condition, we use a quantity called clearness index. So clearness index is actually an index that exhibits the atmospheric clearness. So zero, if the clearness index equals zero, so this implies a full cloud cover condition, and if it is 1, it implies a fully clear sky condition. So for the analysis, we will calculate clearness index for every day in January 2018 to December 2019 for every station. So it is actually called the daily clearness index. And then we will divide it into 3 categories. The first one is the clear sky condition, the second one is the cloudy condition, and the last one would be the overcast condition. So we also applied 2 post-processing methods to the model output. The first one is the spatial interpolation of the model output using the bilinear interpolation, and the second one is the empirical quantile mapping. So the quantile mapping is actually a method that we use to create a transfer function between the observed data to the model data based on its probabilistic distribution. So for the empirical quantile mapping, we use the observation data and model output or hindcast in 2018 as training data. And then the correction is done to the forecast that is generated from January to July 2019. So to assess the performance of the bias correction method, the empirical quantile mapping method to bias correct the model output, here we define two parameters. The first one is alpha, that represent the mean error ratio, and the second one is beta, which represent the standard deviation ratio. So if the error after the bias correction process is lower than before the correction process, then alpha value should be lower than 1. And if the spread of the ensemble forecast is lower after the bias correction process, the beta value should be lower than 1 too. So here are some of the results. So from the calculation of several error metrics under different cloud covers, we found that correlation value decreases with increasing cloud cover, which is not so surprising. But one of the interesting things is that it turns out the model tends to underestimate the daily radiation when the cloud cover is minimum, that is indicated by negative mean bias error values, and overestimate it during overcast days. So from previous studies, we expect that this is caused by the underrepresented cloud fraction in the model. So this is the visualization of the data before and after the correction method. So there are 6 gray boxes in this slide. So in the first gray boxes, the left graph is the monthly value of radiation that is generated in January 2019 before the bias correction method, and the right one is the same forecast for the same period but after the correction method. So this one is for January, this one is for February, March, April, May, and June. So from the visual inspection only, it can be seen that after the bias correction method, most of the time the ensemble average tend to get closer to the observation value, which is the yellow lines in every graph. So from the visual inspection only, we can expect that maybe the bias correction method did provide better accuracy, but to make sure, we also have to see from the quantitative assessment. So here we plot the value of alpha and beta in every station for every lead time and for every initial running time. So improvements are shown if the value of alpha and beta are less than 1. And despite some outliers, the alpha value in all stations is lower than 1 for most initial running time and lead time. However, the bias correction technique did not necessarily reduce the spread of the forecast because we still see a lot of beta values are actually higher than 1. So here are some of the conclusions. So the first one is the evaluation results show that larger correlation value is seen on clear sky condition and an increase in the amount of cloud cover associated with a decrease in the correlation value. The second, in sunny days, the model tends to underestimate the actual solar radiation. Meanwhile, in dark days, the model tends to overestimate the actual solar radiation. And the last one would be empirical quantile mapping method did provide better accuracy, but not necessarily better precision. So that's all for today, and thank you for listening to my presentation, and see you again in the discussion session.